Hello and welcome to my talk today. My name is Alexander Lobbe, and I'm happy to be presenting today at the online ISDA conference on machine learning and data simulation. First of all, I would like to thank the organizers for inviting me to give this presentation. I will be speaking about Bayesian inference for geophysical fluid dynamics using generative models, which is a work that we performed in the ERC Stewart project at Imperial College London. And this is a joint project together with Dan Crisan and Oana. So first of all, I would like to present to you what is the outline of the talk. So the goal of the overall project is to generate a skillful ensemble forecast for a fluid dynamics model by using a trained noise generator. And I will specify exactly what this means a little bit later. And also we want to assess the stochastic model performance by data assimilation. And our tool to do that is the particle filter. So first of all, I will introduce the model that we are using, which is a rotating shallow water model, and the corresponding stochastic parameterization. Second, I will introduce the specific learned noise generator, which is based on a score-based generative model via diffusion Schrödinger bridge algorithm. And then I will show you the results on the ensemble forecast scoring using the noise that we have trained. And finally, I will present the results from the particle filter. So the model that we are using is a non-dimensionalized rotating shallow water model, and I've written out the equations on this slide. What is interesting to note is that we are using a wind forcing on a two-dimensional domain and also a quadratic drag term. The non-dimensionalization has helped us in the sense that we are able to change the Rossby and Frude number in order to change the properties of the flow, which simplified experimentation for us. And the specific flow parameters that we are using here is we are using a Frude number of 1.1 and a Rossby number of 0.2. And we have chosen a beta plane approximation with a specific parameter beta 0.001 and some numerical diffusion as well. And the model is run on a unit square with a spatial step size of 1 over 128, and the time step is 0.0001 on a doublet periodic boundary. So our setup is such that we are running our model on two different scales. One is a fine scale and one is a coarse scale. And in order to be able to observe a difference, we need to have a flow that has features which are present in the fine run but not in the coarse run, so that the stochastic model can be used to compensate for that difference. And this is just a confirmation of the presence of such features. So in the bottom row on this slide, you can see on the left a snapshot of the height variable of the shallow water model when we run the PDE on the fine grid. And in the middle is a snapshot of the same field, but using a low pass filter to cancel out the high frequencies. So that's why it appears blurry. And on the third picture, we can see the PDE run on the coarse grid from the same initial condition as the fine PDE. And we can see on the top that the root mean square error between the fine runs, so the black line is the filtered PDE, which corresponds to B on the fine grid, versus the evolution of the coarse PDE. And the red line is the fine PDE without the filter compared to the coarse PDE. And we can see that the root mean square error grows, so that we confirm that the runs on the two grids indeed diverge over time. And there is something there will be a term to model in order to bring the evolution of the coarse PDE closer to the evolution on the fine grid. And the way that we are trying to achieve this is by using a stochastic parameterization. So the idea is to account for the unresolved scales in the coarse grid via a stochastic term on the coarse grid model. And this term has to be calibrated. So the equations for this model, they are on the slide here, the top two equations. And you can see the red term, that's the noise term or the random term that we introduce, which gives us a chance to calibrate the model so that we can stay closer to the evolution on the fine grid of the PDE without any noise. And the way we do this is we run the PDE on the fine grid and record as data the height fields. And now there is a specific way in order to use this data to calibrate the noise term in the coarse grid stochastic model. And you can see the equations on this slide. The bottom line is that we need to calibrate the random variable psi from the height data. Specifically, we need to collect the difference between the fine fields and the smooth fine fields using coarsening operator, which is a low pass filter, and then model the increment in time, which is the m hat t plus delta minus m hat t. And this is given by a random term psi, which is on this slide. Now you can observe that this term psi includes Brownian motion, which means it's Gaussian. But since this assumption is not always true in practice, we would like to have a model which allows us to model closer to the data by relaxing the Gaussian assumption. Hence, we make the ansatz that the perturbation here, which is the data, can be modeled by a stochastic representation, including a PDE term curly m and a random variable capital N, which has an unknown distribution that will be replaced by a generative model. And one assumption we need to make is that the distribution of our noise is stationary, as the generative model, specifically the diffusion model that we use, can only sample from a fixed data distribution. And one of the technical details is that when we train the model, we can take the perpendicular gradient of the output of that model, which then represents a velocity perturbation for the stochastic model. So what does the data look like that we obtain from the equation for this capital psi on the earlier slide? So what we need to do is we need to solve an equation in each step to obtain a realization of this psi. And for our run, we do this almost 15,000 times for 15,000 data points using a finite difference solver, which is constrained to yield mean zero solutions. And in order to make it easier for the model to learn, we transform the data using what's known as an arcsine H transformation. And we scale the data set to the range 0, 1, which are standard operations in machine learning. And on the bottom now, you can see the distribution of the data which we intend to model by the generative model. Note that this is an overall distribution over all the pixels. So it's the spatial component has been eliminated in this summary distribution. So it's not a one-dimensional distribution that looks like this that we are actually modeling, but it's a distribution over a spatial field, and you can think of an image distribution. And this is just a distribution of all the pixels taken together. So the model that we've chosen to do this is a specific version of a score-based diffusion model known as a diffusion Schrödinger bridge model. This has been developed originally by De Bortoli, Thornton, Heng, and Doucet. And typically, if you look at the figure on this slide, training a diffusion model involves training a forward process and a backward process, where the forward process is a suitable way to induce noise to the data. And then the backward process takes as input a new noise sample from that distribution and then generates a new sample point from the distribution of the data. One difficulty is to choose a suitably long noising path and denoising path. And that's where the diffusion Schrödinger bridge model comes in. We can choose a shorter path and iterate the whole procedure using this Schrödinger bridge approach. So that means that we can deal with shorter noising path and improve on a first training of the diffusion model iteratively. And this is what it looks like for us. So the metric that we're using to assess the quality of the generative model is the Fréchet inception distance, which is standard in image generation. And it models the distance between the distributions that are output by the generative model and the distribution of the data. Here, lower FID scores mean that the model is closer, the model distribution is closer to the data distribution. And we can see on the left graph that after only a few iterations of the diffusion-Schrödinger bridge procedure, the FID score improves drastically, but then deteriorates after a while, which is expected and has also been observed by the original developers of the DSP model. And on the right, we see again the reduced representation of the distribution in one dimension. So the blue curve, that's the distribution of the pixels in the data, and all the other curves represent the different output distributions of the diffusion-Schrödinger bridge model after various numbers of iterations of the DSP steps. And we can see the orange line, which offers the best FID score, is also visually the closest to the data distribution. One difference that we can see for all of the DSP models is that they put significantly more mass on the mean value. So here I have I'm showing some samples of the training data and the data generated by the diffusion-Schrödinger bridge model. On the left, we see the training data, and on the right, we see the generated data. And you can see as there is a lot more purple in the plots, that's the mass on the mean. But otherwise, we can see that the spatial structures seem to be matched. Now we want to assess the ensemble forecast for our stochastic model using ensemble forecast metrics. To do that, we consider three different scenarios, different forecast horizons, which is one short horizon corresponding to 1,000 time steps, a medium horizon of 2,000 time steps, and a long horizon of 4,000 time steps. And in each case, we run the model over a total of 4,000 time steps. So that means that we repeat the short forecast 1,000 times, the short forecast 4 times and the medium forecast 2 times. We select the same strength of the noise for all experiments. So there's a little variance parameter that we can set, and this is set the same for all of the experiments. And we average the reported scores over space, and where applicable also over the repetitions. So we are using two different metrics. One is the CRPS score, which is the continuous rank probability score, comparing the two distributions, and we are also using the rank histograms. So for the CRPS score, we can observe in the table on this slide that the forecast horizon of 1,000 steps offers the best CRPS scores for the variable height in the model, but the best forecasts for the velocity variables are obtained for the medium horizon of 2,000 steps. This is also reflected in the rank histograms on the right. So we can see that the top left histogram for the height with a short forecast horizon is the most flat of the three ones on the top row for H. So that means that this gives us the best forecast ensemble for H. And for the velocity variables U and V, we can see in the second and third rows respectively, the flattest histograms appear to be the ones in the middle for the medium forecast. Now for the data assimilation experiments, the setup is we run the SPDE ensemble over 400 time steps with an observation noise parameter of 0.01. And we compare the results for different numbers of ensemble members, different observation dimensions, and numbers of forecast steps. In the table here, we have reported the bias of the ensemble. And we can see that for different dimensions of the observation, and a different number of ensemble members, we observe that we obtain biases which are close to the observation standard deviations, which in conclusion gives us the conclusion that the ensemble has been effective. And here are some evolutions. So this is a sample evolution at a specific point in time, hence 1D, where the true path is the red line, the observations are the yellow stars, and the ensemble is gray. The ensemble mean is plotted in black, and we can see that the ensemble tracks the truth and that the particle filter is effective on pulling the distribution back to the truth. Also, we look at the bias and RMSE, and we observe again that the values are close to the sigma ops, which is optimal. Now for filtering on various coarsening levels. So now we have used a coarsening level of 32 by 32 in the previous results, and we want to check if higher or lower coarsening achieves better results. And in fact, that's not the case. So if we compare our coarsening to the coarsening to a higher coarsening, to a lower coarsening, meaning better resolution in the coarse run, we see that we do not obtain better numbers for the bias and the average, and also not any better tracking. So it's not necessary to spend any extra compute. And for a higher coarsening, higher coarsening, meaning that the grid for the coarse grid is coarser, we see that it's much harder for the filter, and even with favorable parameters, it's hard to track, and it diverges in the end. So in conclusion, we see that generative models are useful for the generation of appropriate noise distributions in stochastic models. The generated noise indeed models deviations from Gaussianity. The particle filter gives reasonable results, despite the fact that it's run on a coarser scale than the truth model or the signal. And we can confirm that the 32 by 32 grid is the preferred one in this setup. So thank you for listening to my talk, and I'm happy to answer any questions.